welcome to the 5 o'clock talk in the market share track. This is going to be easy local Windows kernel exploitation. Couple reminders, please silence or turn off your cell phones for the talk. Also in your package you would have received speaker feedback forms. If you can go ahead and fill those out and turn them in at the information desk so we can get feedback on everything. Without any other further ado, here's Cesar.
Hi everyone, thank you for coming. I know this is a really difficult spot of the day, like last talk, everyone wants to go party, drinks, or maybe writing a report, whatever, but it's like everyone is tired, so I will try to be fast and clear. So like the title says, this is a couple of 3 different tricks for exploiting some kind of Windows kernel vulnerabilities. And when I say easy, I really mean it. You will see that every trick requires just some 3 easy steps. You won't even have to think about it, so it should be easy to learn and to understand. So everyone that has been doing Windows kernel exploitation should know that it's not very well documented. It's kind of still of a dark art, we can say. There are very few cool exploits available. Some of them are not reliable. And the same with techniques. There are really good techniques, but the thing is when you go to this kind of vulnerabilities where you can control where to write, also the value you can write sometimes. It's called write-what-where exploitation. There are a few techniques available, a few cool papers, but sometimes the techniques are not generic. They work on some Windows versions, and they don't work on different versions. And they are not generic. Sometimes they require certain scenario to be able to work. And when the things get complicated, they won't just work, because sometimes you have really restricted scenario where the value you can write is not fully controlled by you, by the exploiter. Sometimes you can just write 1 byte to the kernel. Sometimes you can just write null, for instance, to the kernel. Sometimes you can write a fixed value, etc. Or there is some weird scenario where you can just increment a value or decrement a value. So as far as I know, there is no generic way and easy to use technique to exploit this kind of bugs with these difficult scenarios. And one thing in common with all the techniques available right now is that you always end up running code in kernel. I mean, it's cool to run code in kernel, and sometimes it's needed, depending on what you want to do. But you will agree with me that if you make any mistake, then you will get a crash, and there is no second try. I mean, you make a mistake, the code is not stable, and you get an instant crash, a blue screen, and that's it. So it's better for me if you can avoid running code in kernel. So all this research started after I read a really cool paper by Matthew, I don't know, Matthew and the other guy. I'm sorry. It's difficult for me to pronounce the name. And GDT and LDT in Windows kernel vulnerability exploitation. This is a really cool paper where they use the anti-query system information to get the kernel address of the K process structure. So they do some overwriting of these GDT and LDT in order to elevate privilege. I like the paper, but I find the technique a little bit complicated. When I saw this API, I remember that I saw it before, for instance, when analyzing how Windows Process Explorer works. But I never thought that this API could be used for kernel exploitation. And I started to research, and this paper inspired me, because this API is really cool because you get all the kernel addresses from different Windows object structures. For instance, you can get the address of a process, a structure, of a token structure, a thread structure, etc. And you get really useful information. For instance, you get the kernel address here in the object field. Then the object type will tell you if it is a process, a thread, etc. And here you get the process ID to which has an open handle to that object. So basically, you will know where each structure is located in the kernel. So maybe I'm lazy, but I like things to be easy to do, like follow 1, 2, 3, and be able to achieve some goals in a very easy way. And it's more difficult to find ways to make it easy, but once you do it, then things become clear, you save a lot of time, etc. So when I started to research this, I started to think about different scenarios of what I could do if I can know where to write in kernel in order to elevate privileges. Because what you want to do in an exploit, when you are exploiting a kernel vulnerability, is to be able to perform privileged actions in order, of course, to elevate privilege. So one of the questions I asked to myself was, what if I can remove an ACL for a process, for instance? If I can remove an ACL from a process, for instance, LSAS process, I could inject code in that process and elevate privileges. Or I could dump the password hashes from there and then crack them offline or doing some pass the hash, etc. Another question I asked myself was, what if I can set any privilege on a token, on a process token? That would mean instantly elevating privileges, because you know where to write, just change some bytes and instantly get more privileges. And then the other question I asked myself was, what if I can just replace a token from my process? So if I can find a really privileged token and then put it in my exploit, I will be able to just doing one write to elevate privileges. Doing this research, I found out that it's possible to do all of this just doing one write to the kernel and without having to run code in the kernel, which is, I think, is nice. I also asked myself, why do you want always a system shell? Because when you are exploiting a vulnerability, what you want to do is to be able to perform more actions than the ones you are allowed to do. So most of the time, it's not necessary to get a full system shell. You just need to perform some specific privileged action. For instance, if you want to get the password hashes, you just need to be able to dump them. Or if you want to run code, maybe you just need to inject code in some process, get the code run there and elevate privileges. So you just need to do a couple of privileged actions with your exploit and you are done most of the time. So let's start with the first track. So here you can see this is the header of almost, I think, of every object on Windows. Here you can see at the end of this object header is the main body of the sorry. And the main body of the specific kernel structure. For instance, if it is a process, then here the body offset will start the eProcess structure. What I found interesting here is you can see here the security descriptor field. This ends up to be a pointer that points to ACL-related information. And this is fixed across all Windows versions. You just, since Windows 2K, maybe since NT, you just have to subtract like 4 or 8, depending on the architecture. And you end up in this pointer. And I found out if you write null there, you just remove the ACL. And the object becomes ACL free. So basically, for instance, if you get the LSAS process, which is a process that runs under the system account, you get the address of this pointer and just write null there, and instantly that process ends up without any ACL. That means that you will be able to inject code there, read the memory, dump the password hashes, etc. So it becomes very simple. You just need to know the address of this structure, which is very simple. Like I said, with this API, entity query system information, we can get that address. So it's not a problem. So let's see this trick in 3 easy steps. First, what we have to do is to get the target object, we want to set the ACL to null. So it could be a thread if we want to modify the thread, or it can just be a process. So we get the kernel object address using the entity query system information. So we subtract 4 or 8, depending on the architecture, and write null there with our exploit. And instantly that object becomes ACL free. And after that, we perform the privileged action we want on that object. Like I said, if it is LSASS process, we can read the password hashes, insert code, etc. That's like you can see, it's very simple. Let me show you a quick demonstration. In this case, I will manually. I will be removing manually the ACL. And a second. Okay, here we have Process Explorer. I have a shell that is running under a low privilege account, and I try to run Windows Credential Editor, which is a really cool tool that was written by Hernán Ochoa, which allows you to dump the password hashes, pass the hash, and other nice tricks. So I try to run the tool, but because I have a low privilege process, I can't do it, so I get an error. So now, taking a look, here you can see that it's running under low integrity level, so it's a really low privilege process. It almost has access to its own process and nothing else. And if I look at the ACL of the LSASS process, we can see it has the regular ACL, which means that only system and administrator account can access to it. So what I'm going to do is to get the kernel object address from the process structure from the LSASS process. You can see here the process name, and this is the kernel address of the object structure. I'm doing this manually, but you can do it with the API I just described. So I have a Windows debugger session, a kernel debugging session. So I can look at the object. We can see here the handle count, the pointer count, some object header information. So I subtract 4 from that, and I will be accessing directly to the pointer to the ACL. Here is the pointer to the ACL of the LSASS process. So I write null there, and now I try to run again Windows Credential Editor. And you can see this time I can get the password hashes, because now the LSASS process doesn't have any ACL at all. And if we look at it with the Process Explorer, we can see that it doesn't have any ACL. You can see it says no permissions had been set for this. In this case, I have done it manually, but in case you are exploiting something, your exploit will be the one getting the kernel object address and then writing null to there. So let's see now the second trick. Another interesting Windows kernel structure I found is the token privilege structure. This structure is inside the token structure, and it has the same offset on Windows Vista, Windows 7, Windows 8, etc. And it has three different fields inside the structure. One is the present field, the enable field, and the enable by default. This field means these are bit masks. That means that every bit that are set there means that a privilege is present or not. So in the present field, every bit set there means that the privileges that are present in this specific token. And in the enable fields means that the privilege from the present one that are enabled or not. So I can have 5 different privileges, but I can have only one enabled. And then in the last field, we have the enable by default, which means which from the present field, privileges are the one that are enabled or not. What I found interesting is that when Windows checks the token for performing privileged actions on the system, it will only check the enable field. And this is cool because when exploiting a kernel vulnerability, I can just directly write to the enable field and enable the privilege I want. And Windows, when my exploit tries to do privileged action, we just check that field. It won't check if the privilege was present or not. So you can imagine how to exploit a vulnerability using this trick. It becomes very simple because you can get the token address, then you know it's a fixed offset since Windows Vista, and you have these 3 different fields, and you know you have to write on the enable field in order to enable different privileges. So the token structure is different on Windows XP and 2003. There are inside the token structure, there is a LUID and attribute structure, which is a pointer that points at the end of the token structure, which is called variable part. And there, depending on the amount of privilege we have in the process, in the token, we have many LUID and attribute structures. Here, in the attribute fields, we have 3 different values. We have 0 for when the privilege is disabled, 1 when it is enabled by default, and 2 when it is enabled. And then in the LUID structure, we have a number identifying specific privileges. For instance, the privilege number 14 in X is the debug privilege. So if I can arbitrarily set privilege to a token in order to elevate privileges, what privilege could I choose to do it if I'm restricted? Because if I'm not restricted, I can just set all the privilege enabled, and it will be the same as running a system account. Maybe I will need to take some extra step when running code, but it's almost the same. So these are the most powerful privileges on Windows, where you can debug programs, you can do anything on any process. Take ownership allows you to manipulate the ACL of any Windows object. Then, but if you can restore file and directory, then you can overwrite any file on the system. So you can remove, overwrite system file and elevate privileges. Then impersonation privilege allow you to impersonate other accounts. Of course, loading and unloading drivers allow you to load drivers, etc. Those are the most powerful privileges on Windows that maybe you want to set when exploiting a kernel vulnerability using this trick. So let's see it is step by step, this trick. First, what we need to do is to get the primary token kernel address from our exploit process. We can do this by using the anti-query system information API, which is just running it and get search under all the array of results it returns, identify our token, and then get the kernel address. if we can control what to write, we just write, for instance, on Windows Vista, we just write FFFFF, which means if you translate it to binary, it's 1111. And we enable all the privileges. And instantly, we get all the privileges enabled just after one write. But if you have Windows XP or 2003, maybe we can write some specific values. In this case, we can choose, for instance, 14 in X, which means the debug privilege. So we write to token, in this case, is plus A0 in X offset. So we write 14 there, and instantly we get debug privilege on our process token. And after that, of course, you can perform privileged actions. So I was lucky that Tarjay shared with me some vulnerability he found last year, and it was patched by Microsoft. It's a news after free kernel vulnerability that was kind of difficult to exploit because you end up in this instruction where you can decrement a position in memory. You can only control the EAX value. So it only allows you to decrement a position in memory. So if you have to exploit this, I mean, you have to do a lot of reverse engineering in different Windows versions, try to find some stable way, some stable value, and others in kernel memory that you can decrement in order to elevate privileges, etc. It's not simple. I mean, it can be done, but it takes a lot of time and work. So by default, when you run a process on Windows at the offset 84 in X or on the token structure, you have this value, which is 80000 in X, which means is on the enabled privileges on the field enabled privileges on the token privilege structure. If we translate that to binary, we can see that only one privilege is enabled by default, which is the change notify privilege, which is a privilege that almost any process in Windows has. That is the privilege to get notified when a registry change or a file or a folder change. It's a very basic privilege that almost any process in Windows have. So by default, you have this value there. And because I can know that address in kernel, when trying to exploit this vulnerability, if I subtract 1 to that, I end up with 7FFFF. And if I translate that to binary, I end up with 11111, which means loads of privilege enabled, because if you remember, it is a bit mask, the field of that structure. So you can see here that a really difficult to exploit vulnerability becomes really simple. Just find our primary token from the exploit process, put that offset of the token where the privileged enabler are, and get that value decremented, and instantly you get a lot of privileged enabled. Pretty easy. We can see the exploit in action. I don't know why this is so slow. So I have a command shell on a really low privilege, running under low privilege account with low integrity, so there is really basic privileges for the process. So what the exploit does is locate the address of the CMD process. First, I try to run Windows Credential Editor. Again, it fails because I don't have enough privilege to dump the password hashes. So I run the exploits, and what the exploit does is, first, it gets the parent process ID, which is the command shell I'm running from where I'm running the exploit. After that, it gets the parent process primary token kernel address. So it can use that address of the token you remember the vulnerability, it just subtract 1 from there in order to enable the privileges. So in this case, what the exploit does is modifying the privileges of the command shell from which I'm running the exploit. So now, after running the exploit, I run Windows Credential Editor again, and I can dump the password hashes, because now I have a lot of different privileges enabled. On one of those privileges is the debug privilege. So I can access the LSASS process and inject code there and get the password hashes. But there is something interesting here, because, like I said, Windows only checks the enabled privileges. It doesn't check the privileges that are present initially in the token. But if we use Process Explorer to look at the privileges, or the command shell in this case, it will continue showing the same privileges, because Process Explorer only look at that part of the structure where are the privileges present first. If they don't find the privilege present there, it won't check which are enabled or not. So you can see here, doing this trick, you won't be able to notice anything weird with Process Explorer in this case in the command shell process. It looks the same, but actually it has a lot of more privilege enabled than these that are being shown here. So the same vulnerability can be exploited on Windows XP and 2003, but in a different way. By default, on offset A0X on the token structure, we have the audit privilege, which is number 15 in X. But in case we don't have that privilege there, we can set that privilege there, because by default it's present, so we can remove other privilege and make sure we have that privilege enabled there. It's not a problem, and we should do it if we want to have a very reliable exploit and not trust in the default execution. So here you can see we have the value of 15, but if we subtract 1, then we end up with 14, which means the debug privilege. So you can see here again, the same vulnerability on Windows XP and 2003 becomes very easy to exploit, because we can know where this kernel address is, and by subtracting 1 to that kernel position, we are setting the debug privilege to our exploit process, and in this case, we can access any process on the system, inject code, etc. Of course, in case you can do multiple decrements, you can continue decrementing until you get another privilege enabled, like take ownership or other privilege. Or you can increment, you can do the opposite. Right? So let's see now the last trick. Another interesting structure I found is that inside the eProcess structure, which corresponds to each process on Windows, there is a structure called xFastRef token. Actually, this is a structure. It's a pointer, but it's a structure because there are some, I think it was the 3 least significant bytes are used to fast reference counting. Given my test, it seems that if you don't care about that when replacing a token, Windows doesn't crash. It just read the pointer count from the object header here. If you remember, in the object header, from each Windows object, there is a reference count maintained there. So if we have, for instance, a process that the handle to that process object was opened by other process, etc., then you get an incremented count there. So Windows knows where to destroy the object when the count reaches to 0. One common mistake there is in some exploit that use the technique, the well-known technique of replacing the token of the exploit with the system token, is that most of the time people forget about incrementing the reference count. So if you run the exploit many times, you end up with a blue screen, because when the reference count reach to 0, Windows will free the object, but there will be other reference available, and other process will try to access the object, and then you get a blue screen. And that is common on some Windows kernel exploit, but because most of the time people just run the exploit once, they don't notice that it doesn't work when you run it many times. So this, I found this interesting because I thought if I can just directly right there, I will be able to replace a token of my exploit with just one write. I just need to know the token kernel address of a privileged token, in this case from a system token, in order to get full privileges. It ends up that it's not difficult, because you can guess, for instance, what are the system token. If you look at different Windows processes, you know that by default, for instance, some really privileged process like system or LSASS has always some token present there, and you know sometimes there are three processes that have one token always present, and it's assistant or administrator, so you can do some guessing. Another way is by abusing in some interprocess communication mechanisms. Because in Windows, when you do IPC, interprocess communication mechanisms, there is some impersonation taking place. And when you do it from a low privilege process, sometimes you end up with an identity token on your process, on the client process that is doing IPC. And I found out something interesting, that when you are replacing a token, the primary token of a process, Windows doesn't check if the process you are setting there is a identity token, is a primary token, or is an anonymous token. Windows doesn't check that. It just checks the privileges that are present in the token. So it's very easy to get a system identity token. In this case, there is an API called MSI install product. So from a low privilege process, you can call that API. You will need to hook NT open 3 token in order to know where the token is opened and avoid that token to be closed by your process. So you make a copy of that token, so you get a system identity token available for your use. And by using the NT query system information, you get the kernel address of that token. So now you have information needed that will allow you to replace the current token of your exploit. Because, of course, if you are exploiting something, you are running under a low privilege account, so you get this system token, you replace your primary token, and then elevate privileges. But, like I said, you must take care of the reference count. Because if you remember, all this is without running any code in kernel. We are just doing one write to the kernel, and that's it. In this case, we will need to do maybe 2 writes, because first, we will need to increment the reference count to a really high value in order to make sure it will never reach to 0. So the first write will be to increment the value, and the second write to replace the token, and that's it. Then you have a system process running. But if you have only one write, there is a solution also, because what you have to do is just replace the token, and then with the second write, you have to duplicate, after elevating privileges, you can duplicate that token in a process that never terminates, like LSASS. Because when you duplicate that, you make sure that process, that token will never be destroyed by the system. So you will the reference count never will reach to 0, so you won't get a blue screen. So like I said, it's a 3 easy step, like get the identity token, get your token kernel address, replace it in your process, in this case it will be the exploit, and instantly elevate privileges. Just make sure to to take care of the reference count. So some final conclusions is like I said, it's really simple. Just calling entry query system information, locate the kernel address, and just write a value at the proper address and instantly elevate privileges. It's just one write. You don't have to run any code in kernel, and that's it. And also it works for really difficult to exploit vulnerabilities. And of course, these are just some ways I found by researching some specific kernel structure. If you continue doing some research, maybe you can find some even easier way to elevate privilege by replacing some values in some Windows kernel object structure. And finally, like I said, for me, it's like you don't always need a system share. You just need to be able to perform privileged actions. So there is a reference to the paper, and thanks to Ruben Santamarta and Tarshade for the feedback and proof of concept. That's it. So, any questions? Questions? No? Okay, so it was easy, right? Thank you.